Hello guys, welcome to my channel. In this video we will see what is a test bench, how to write a simple test bench, the difference between logical and bitwise operators. So far we have seen how to write Verilog modules for any combination circuit, which is nothing but we are making the design entry. We are describing the functionality of a hardware in a language that our computers can interpret. This is how physical testing of a digital circuit would look like. This is an IC which we place it on a breadboard where we can use the wires and make the connections. After connection, we power it up with a signal generator which produces signals or voltage levels that we require, and for outputs we probe them and connect them to the oscilloscope. Oscilloscope can detect our signals, can read our signals. So this is the display of our oscilloscope which displays our outputs. So when it comes to our HDL thing, test bench is where we apply inputs to our modules, such as stimulus to our modules. After writing a module, we have to test whether it's working well or not. So in the test bench, we create waveforms for inputs and apply them to our modules. Test bench doesn't have input or output port list. Our modules has. Modules are the one which takes in inputs and creates certain outputs. But in the test bench, we are defining the sequence of inputs, what it has to be, and we will apply these inputs to the modules. The inputs of the modules are declared with keyword reg, which means for register here, and the outputs are declared with keyword wire. Module has to be instantiated in our test bench so that the test bench will give the inputs waveforms that we are generating in this to that particular module. This is a simple module describing the AND gate where the inputs are A and B, output is out. Let's try writing a test bench for this. This is the general syntax of a test bench. Test bench is also enclosed within the keywords module and end module. And we are naming an output with t underscore out. The inputs are t underscore A, t underscore B. And the module has to be instantiated here. So we do it by using the same name of the module. And underscore gate is the name of the module. We put the name here. We give a name for the module. M1 is the instance name here. And we give the port list in the same order but with different variable names. So t underscore A corresponds to A here. The first one here corresponds to the first one here. The second one here corresponds to second one here. And the t underscore out, which is third one here, corresponds to this. Since A and B are inputs, they are declared with keyword registers. Out is the output which corresponds to t underscore out. It is declared with keyword wire. After doing all these things, we will generate the stimulus for t underscore A and t underscore B, which are inputs. So all our signals are time valued signals. That is, our signal will have a particular value at one instance of time. Later, it may have a different value or same. So the signals are defined with respect to time. For this, we specify time without any dimensions with a hash symbol. Hash 10 represents 10 units of time. We can also specify what 1 unit of time would correspond to in our physical time. I mean, should 1 unit of time be 1 second, 1 millisecond, or it is 1 microsecond, what it is exactly. You can define what you want it to be. You can do that with a compiler directive which is backcode timescale. Compiler directives are the directives which tell the compiler what it has to do during the simulation. Suppose if I do backcode timescale 1 nanosecond slash 100 picoseconds, it means 1 nanosecond is 1 unit of time. 1 picosecond is the precision to which the things are rounded off. So if I do this, hashtag 10 would mean 10 units of time, which is 10 nanoseconds in our real life. The waveforms which we generally describe are in the initial statements, which are enclosed by keywords begin and end. The statements in the begin are executed in a particular order. The leftmost one will be executed first, then the right one. The top statement will be executed first and then the bottom one. Hash n represents certain units of time. In this, it would generally represent n units of delay. So if you look at this initial, so we are starting something. Begin says to begin the simulation. A is equal to 1B0, which means it's a 1-bit binary 0. Here it says A is equal to 1B1, which means it's a 1-bit binary 1. A will become 1-bit 0 and B will become 1-bit 0 as soon as the simulation starts. So at t is equal to 0. Then it comes to next line. It says hash 10. So a delay of 10 units. Our simulator waits for 10 units before it executes the next statement. It moves right. It says A is equal to 1B1, B is equal to 1B1. So our simulator will make A and B as 1-bit 1. It goes to the next line. It says end, defining the waveforms in this set is ended here. In this line, it says initial hash 10 finish. Finish specifies termination of simulation. Our simulation ends there. So if you look at it again, as soon as our simulation starts, A and B will be 1B0. A and B are 0 at t is equal to 0. Then next line says wait for 10 seconds, delay of 10 units. So it stays at 0 for 10 units of time. Both A and B are 0 for 10 units of time. Then both A and B are 1B1, which are 1-bit binary ones, 1 and 1 after 10 seconds. This statement says delay of 10. So it waits for a delay of 10. Finish specifies the termination of simulation. Our simulation ends here. This is how the waveforms would look like with these statements. Now let's look at the propagation delay of a gate. This is an OR gate and this is its truth table, which mentions if either of its inputs is 1, the output will become 1. Now suppose B is 0 the whole time and A is 0 initially and A becomes 1 at this point of time. The output of the gate doesn't become 1 instantaneously as soon as the A becomes 1. It takes certain time, which is called as propagation delay. Let's see how you can include the propagation delay in the code. So suppose our propagation delay is 3 units of time. So in the module declaration, while you are assigning the outputs with its inputs, you just mention hash in the braces the propagation delay. Same way you can do it while doing the Boolean expressions also. Now let's see the difference between logical and bitwise operators. As I mentioned in the last video also, logical operators works on Boolean values and it returns Boolean values only, whereas bitwise operators work on specific data type and it returns the same data type. Let's try to understand them in more detail. Logical operators looks at the values in terms of Boolean expressions or Boolean values. What it means is, if the value is 0, which means all the bits are 0, it considers it as a false expression. If even one of the bit in the number or in the value is non-zero, the whole number will become non-zero, so it considers it as true value. False is treated as 1-bit 0, true is treated as 1-bit 1. Bitwise operators operate bitwise. They just look at 1 bit at a time. Let's understand this with examples. Suppose A is a 4-bit binary 0101 and B is a 4-bit binary 0001. Here A, logical and B will give us the answer 1-bit 1 because A is non-zero, B is non-zero. Both of them are true. So A is treated as 1-bit 1, B is treated as 1-bit 1. Here you are ANDing 1-bit 1 with a 1-bit 1. The result would be 1-bit 1. If you want to understand it in different terms, both A and B are true. AND of true and true is true. So it is 1 bit 1. I prefer looking at them as boolean values 1 bit 0, 1 bit 1. I try assigning 1 bit 0, 1 bit 1 with true and false statements, and then I try to work. Whereas bitwise AND will just look at bitwise things. AND of 1 and 1 is 1, AND of 0 comma 0 is 0, AND of 1 comma 0 is 0, AND of 0 comma 0 is 0. So A bitwise AND B would give us this answer. Let's see more examples. Suppose A is 4 bit 0101 and B is 4 bit 0000. A has non-zero bits, so A is true. B is 0, all the bits are 0, so B is treated as false. If you do A logical and B, it would give us 1b 0, AND of true and false, or like AND of 1b 1 comma 1b 0. If you do bitwise operation also, you would get the same thing. If you do logical operation, or it's like OR of true comma false, or OR of 1 bit 1 or 1 bit 0, so which is again 1 bit 1. For OR to be 1, one of its inputs can be 1. That is a sufficient thing. So if you look at bitwise operator A or B, the answer would be 0101. As you can see here, 1 or 0 is 1, 0 or 0 is 0, 1 or 0 is 1, 0 or 0 is 0. So that is the difference. Even if you are operating with 4-bit numbers here, when you do logical operator, you will get a 1-bit output. Whereas bitwise operator returns the same data type. Logical operator works as Boolean value. It looks at the whole value. Bitwise operator just looks at bitwise and returns the same data type. In our earlier module, we have used logical operators for AND or NOT, etc. But using bitwise is also okay. It is preferred to use logical operators just as a good programming practice. If you look at what happens with the gates or any combinational circuits, or for any digital circuit, the inputs are 1-bit numbers. You won't give 2-bit numbers as inputs. There is only logic low, logic high. There are no intermediate binary values between logic low and logic high. It is just a good programming practice to use logical operators. You can use bitwise operators also. The result would be same because A and B, or the inputs of any combinational circuit, are 1-bit inputs. So far we have seen how to write a module, how to give the waveforms for inputs for a module, that is Testbench. Now we have to see our output. Our output can be time ordered sequence of signals, or we look at the waveforms and understand. So this is how we test the functionality of circuit even before the fabrication of hardware. What this fabrication and all means is getting the IC, putting it on a breadboard, wiring it up, using a signal generator to power it up, and then using an oscilloscope to read it. Instead of doing all these things, you can write a module, you can give the waveforms for inputs in the test bench and test it. So in our next video, we will see how to display the output, and I will also mention some efficient ways of writing a module, which are like simpler ways of writing a module and test benches. And I will tell you where you can simulate Verilog code. One is Vivado from Xilinx, and there is one more software called iVerilog, which you would need command prompt to simulate. And there is one free online platform which is EDA Playground, edaplayground.com. So you can do your simulations in any of these things. So we will look at them in detail in our next video, where we will discuss how to display the output and what are the efficient ways of writing a module and test benches. Stay tuned by subscribing. Thank you.